Hello friends, welcome to engineering tutorial. Now in my previous video I discussed about the series and parallel combination of resistance, circuits related to series and parallel combination of resistance, and we determined the expression for equivalent resistance across a series circuit and a parallel circuit. Okay, we mostly dealt with resistors, okay, series and parallel connection of resistors. So in today's video we are going to discuss about a concept which is related to parallel connection of resistors. Okay, it is related to parallel connection of resistors. So the concept is called as current division rule. Now the first thing related to current division rule is that it is only applicable for resistors connected in parallel, and its purpose is to determine current flowing through parallelly connected resistors. So here you can see is a basic circuit employing two parallelly connected resistors R1 and R2. They are in parallel connection. You can say that they are in parallel because the two ends of the resistor are connected at one common point. Both of the two ends of the resistors are connected at one common point, okay, and then it is connected across a voltage source, okay, V. It is a DC voltage source. Here I, capital I, is the total current of the circuit, and I1 and I2 are the currents flowing through resistors R1 and R2. Now the utilization of the current division rule is to find out these currents I1 and I2 flowing through resistors R1 and R2. Okay, so the current division rule is used to determine these currents I1 and I2. So first we will just look at the expression for determining these currents, the formula, and then we will go to the derivation part. So according to the current division rule, the current flowing through resistor R1, which is I subscript 1, is given by this expression: total circuit current I into resistor R2, this resistor, divided by R1 plus R2. This is the expression for this current I1, the formula for determining this current I1 flowing through resistor R1. And the current I2 is given by the expression I into R1 by R1 plus R2. So here the interesting thing that you can notice here is the total circuit current is multiplied with the opposite resistor. Here the current flowing through R1 we have to determine, but in the numerator you will find the opposite resistor, the other resistor R2. Similarly, here we have to determine the current flowing through resistor R2, but here in the numerator we are multiplying it with the other resistor R1. The denominator remains the same in both of the expressions, that is R1 plus R2, but here there is a high chance of making a mistake. Most of the students, they multiply I with R1 and I with R2 while determining I1 and I2, but it is a mistake. While determining I1 in the numerator there will be R2, while determining I2 in the numerator there will be R1. So most of the students, what they do is, while calculating I1, they write it as I into R1 by R1 plus R2, and I2 is equal to I into R2 by R1 plus R2. So it is a mistake, it will be wrong. So always remember, the current flowing through a particular resistor in parallel by current division rule is the total circuit current multiplied with the other resistance divided by the sum of the two resistors. Okay, so this is the formula for determining the currents I1 and I2 flowing through resistors R1 and R2 according to current division rule. Now we are going to find out how we derived these expressions, how we got these expressions. So we go to the mathematical derivation part. So now we will see how we derived the expressions of the current division rule. So we have used the same parallelly connected circuit employing two resistors R1 and R2 across a voltage source, a DC voltage source V. So I, capital I, is the total circuit current. I1 and I2 are the currents flowing through the resistors R1 and R2. Now we have already studied from parallel combination of resistors that the equivalent resistance of a parallel combination is the reciprocal, the sum of the reciprocals of the individual resistance. So we calculate R equivalent is equal to R1 R2 by R1 plus R2. That is the equivalent resistance of parallel combination of resistors. Okay, it is the formula for equivalent resistance of a parallel combination of resistors. Now the voltage across R1 and R2 will be the same and it will be equal to the DC supply voltage V. Why? Because when resistors are connected in parallel, the voltage across them remains constant. It will be the same. So whatever will be the voltage drop across R1, that will be the voltage drop across R2. So VR1 and VR2 will be the same and it will be equal to the DC supply voltage V. The voltage drop across R1 is equal to V and the voltage drop across R2 is also equal to V. Now we can also write the voltage drop across R1 as I1 into R1, okay, product of current and resistance. Similarly, the voltage drop across R2, we can write it as I2 into R2 and they are equal to the DC supply voltage V as they are connected in parallel across the DC supply voltage. So this is the expression number 2, we will mark it as 2. This is equation number 1 and this is equation number 2. Now if we have to calculate the total circuit current I, it is given by the expression I is equal to V by R equivalent. That is, total circuit current is equal to the DC supply voltage divided by the total resistance of the circuit or the equivalent resistance of the circuit, which is this R1 R2 by R1 plus R2. So again, just let us pay attention to each of the three equations that we just got. R equivalent is the equivalent resistance of the parallel combination of resistors, that is R1 R2 by R1 plus R2. Next, the voltage drop across the resistors R1 and R2 will be the same as they are connected in parallel across the DC supply V. So each of the voltage drops will be the same, which is be equal to V, and the voltage drop can be also written by the expression of the product of the individual branch currents and the resistance values. That is, VR1 is I1 R1 and VR2 is I2 R2. Next, the total circuit current I is equal to the DC supply voltage V by the total resistance of the circuit, which is the equivalent resistance of the parallel combination of resistors. Now, if we put equation 1 and equation 2 in this 3, it means we substitute V as I1 R1, okay, we substitute V as I1 R1 and we substitute R equivalent with this expression R1 R2 by R1 plus R2. So we have substituted here I is equal to V by R equivalent. So we substituted V with I1 R1 here, I1 R1, and we substituted R equivalent with R1 R2 by R1 plus R2. So here this R1 plus R2 goes to the numerator, I1 into R1 plus R2 divided by R1 R2. R1 and R1 gets cancelled as they are present in both the numerator and the denominator. So we get the total circuit current I is equal to I1 into R1 plus R2 by R2. Now if we take this whole expression R1 plus R2 by R2 towards the LHS, we can calculate the value of the current I1. That is, I1 is equal to, this whole goes to the LHS side, that is I into R2 by R1 plus R2. So the current flowing through the resistor R1, that is I1, is equal to the total circuit current multiplied with the other resistance, okay, the other resistance divided by the sum of the two parallel connected resistors, R1 plus R2. So here we substituted this V with I1 R1. We substituted V with I1 R1. If we substitute V with I2 R2, in this V, if we substitute V with I2 R2 and R equivalent with this, we will get the expression for this current flowing through resistor R2, and it will be I2 is equal to I into R1 by R1 plus R2. Here for calculation of I1, we substituted V, this V, with I1 R1. We have to calculate, for calculation of this current I2, we have to substitute V with I2 R2. Both of them are the same, the values are the same, but just for derivation purpose, we have to substitute V with I2 R2, and this will remain the same. Then we will get the value of I2 as I into R1 by R1 plus R2. So here we have derived the expression for I1, and similarly we will get the value of I2 just by substituting V is equal to I2 R2. So you can substitute that just in this way, and if you get this expression for I2 as I into R1 by R1 plus R2, then you are correct. Okay, so here we have derived the expression for the current division rule. Okay, so let us derive the other expression for the current flowing through the resistor R2. As I said, for that we have to substitute V in this expression V as I2 R2, and this R equivalent will stay the same, this. So here we have substituted this V with I2 R2, okay, and R equivalent is this R1 R2 by R1 plus R2. So here again this R1 plus R2, this goes to the numerator, so it becomes I2 R2 into R1 plus R2 by R1 R2. R2 R2 gets cancelled from both the denominator and the numerator, so we get the total circuit current I is equal to I2 into R1 plus R2 by R1. Again this R1 plus R2 by R1, this part we will take to the LHS side, so we can calculate, we have to isolate this I2 value, so we calculate the value of I2 and we get I2 is equal to I into R1 by R1 plus R2. So here for calculation of I2, we substituted V with I2 R2. For calculation of I1, we substituted V with I1 and R1 in this expression. And we have already calculated the equivalent resistance value, which is R1 R2 by R1 plus R2. This is the equivalent resistance formula for parallel combination of resistors. So here we got the current flowing through the resistor R2 as total circuit current multiplied with the resistor R1 divided by the sum of the resistances R1 plus R2. Okay. So another important thing associated with the current division rule is that whenever you apply current division rule in any circuit, okay, here it is a simple circuit that we just used to demonstrate the current division rule application, but whenever you apply current division rule in a complex circuit, always make sure that the structure to which you are applying the current division rule, the resistive structure, it is always in this form: two resistors connected in parallel, in this form, with current, a total circuit current flowing, and it gets divided into two currents flowing through each of the two resistors. So this will be the ideal circuit structure, the perfect circuit structure for application of current division rule. So always whenever you apply current division rule in a circuit, in any complicated circuit involving many resistors, always try to reduce the circuit by calculating the equivalent resistance reduction method. Reduce the circuit, bring it into this form, in the form of two resistors connected in parallel, and then you can easily find the current flowing through each of the resistors, the two resistors, and then you can subsequently find the individual branch currents. I will demonstrate this with the help of many circuit problems in my upcoming videos, but for now you just understand that whenever you have to apply current division rule, you have to make sure that the circuit structure is in this form. two resistors connected in parallel, the current division takes place at a particular node because current division rule can only be applied to a parallel connection circuit. Resistors connected in parallel. Another important thing, most of the time it is very easy to make this mistake. Okay, it is very easy, especially when you are beginning with this current division rule, you are starting to with this subject. It is very easy to make this mistake, that is current I1 is equal to I into R1 by R1 plus R2 and current I2 is equal to I into R2 by R1 plus R2. It is very easy to make this mistake, and most of the time students make this mistake, but actually this is wrong. It is wrong. I1 is equal to I into R2 by R1 plus R2, I2 is equal to I into R1 by R1 plus R2. So the trick here is that the total circuit current is multiplied with the opposite resistor, okay, other resistor than the current which you have to determine through the particular resistor. Okay, it is always the other resistor, not the same resistor. Suppose you have to find the current flowing through R1, that is I1, you have to multiply it, the total circuit current, with the other resistor R2, and the denominator is the same in both the cases, R1 plus R2, that is fixed. But in this numerator part people make mistake. For calculating I1 they multiply here with R1, for calculating I2 they multiply it with R2. This is wrong. So it is always the other resistance value with which the total circuit current is multiplied in the numerator. For I1 it is I into R2 by R1 plus R2. For calculation of I2 it is I into R1 by R1 plus R2. So please take care of this thing. Okay, practice it, practice writing this as many times as you can until you get it right, and then it will be okay, it will be all right. So here we have demonstrated the current division rule, the formula for current division rule and its mathematical derivation. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, communication and instrumentation engineering. Have a great day. Thank you very much.